Geneva and out of the Finger Lakes region experienced some of these amazing places that have a variety of things we talk about. And so we came up with this idea, and then with the rest of our colleagues in the department, decided to form this geoscience field tour course. We call it Geo 299. That's the number for the course. And over the years, we've gone to a variety of places with groups of students that usually range in number from 10 to about 20. And you can imagine some of the places that draw the larger numbers, like the Bahamas and Hawaii. The big island of Hawaii, we've taken 2 groups out there, Bahamas a number of times. And then me and Nick have led the storm chase out to the Great Plains and the Central Plains area of the US and the Midwest 3 times. And so we've had a variety of groups. We've also gone to other places around the country, Pacific Northwest, and a few places out in the Rockies. So it's really been a successful type of situation here. We just want to share a little bit about what we actually see in play here. And this is video from our last field course storm chasing. And down here, sort of in the central part of the panel, we see a fairly large tornado. It's what we call a multi-vortex tornado. There's actually multiple tornadoes within this larger tornado rotating. You can't see the smaller ones embedded. And it's on the ground. It's causing damage at this point, and we're sitting and watching it. And out the window, we're in the vans at this point because there is some lightning going on along with the storm. But this is an amazing day. And if it wasn't for the students that forecasted and sort of directed us to this storm on this day, we would have missed this great storm. So this is a great example of one of those sort of classic days that we hope to see when we go out in the storm chase. What we're going to do is share a little bit about the field course and the sort of structure of it with you, and a little bit about severe storms themselves. And how do, where do we start? Well, we don't sort of rush right off of campus out in the field and start getting out to the tornadoes, because students are joining the field course from a variety of experiences. That is, students that have maybe just taken the intro meteorology course, or students that have taken a variety of weather and climate courses that we offer in the department, ranging from first-year students to seniors. And so we start on campus actually for 3 days. It's sort of an intensive workshop that we run, and we collect some of our own observations and practice those. And in the upper photo here, we're actually collecting what's called the Ravensson observations. It's a weather balloon. We attach an instrument. We're fortunate to have one of those mobile systems on campus with us, and we can take that with to our field course and collect some of our own measurements while we're chasing storms. And then we actually do some classroom work. And that varies from lecture-based, talking about the structure and the conditions that lead to severe thunderstorms and tornadoes, to actually introducing students to paper atlases, believe it or not, sort of old school stuff, right? To show them, because some places we get out in the middle of nowhere, there is no cell phone service. We can't rely on GPS necessarily to know exactly the road network. So we bring a stack of road atlases with us, and we like to introduce them to that idea, as well as how to use them to chase storms, be at certain places at certain times, and so on, using the road. So we've developed a whole series of workshops for them to introduce themselves to a variety of things related to storm chasing. Storms themselves, in terms of tornadoes, can really range in terms of their intensity and strength. And they're measured sort of indirectly in terms of the intensity. So tornadoes are measured by the amount of damage they actually cause during their situation.
Yeah.
And they range in what's called the enhanced Fujita scale. That ranges from 0 to a rating of 5. And so that can lead to light damage, something on the order of wind speeds estimated from 65 to 85 miles an hour. So that's actually the wind speed that would get you into hurricane status for a whole different types of storm. And the incredible damage on an EF5 scale, which are much more rare. You can see the percentage of occurrences in the United States of each of these EF scales or intensity of tornadoes. EF5 is less than 0.5% of all tornadoes that occur in the US. And those winds can be above 200 miles an hour and cause significant amount of structural damage, basically level any kind of structural building that they may encounter. The structure of a storm, what we're doing is looking down from the top on top of a severe thunderstorm here. And most of the tornadoes in the US develop what we call from supercell thunderstorms. This is a thunderstorm that has rotation within it in its updraft region. That would be in that central part where Nick is using the cursor there. And the yellow and the reds and the greens here represents area of precipitation that you would see associated with a storm if you're observing it from a radar. We'll look at one of those in a second. So there's a forward part of the storm that sort of leads the direction that it goes towards the northeast. So these storms sort of move in regular sort of fashion from southwest to northeast after they develop. And then there's a rear part of the storm where in both of these areas you have significant air that is rushing towards the surface. And those are straddling that updraft region that is rotating. And in this updraft region is most likely the direction or location in the storm where you'd see a tornado if a supercell storm developed a tornado. And it sort of descends from cloud base towards the surface.
If I can just add real,
supercells,
can I just add real quick, Neil, that one of the most common questions we get obviously is about safety, right? You know, we have students, we have Neil and myself, you know, safety is #1 priority. And it's all about knowing what you're doing, right? You know, if you know the storm is moving southwest to northeast and you know the tornado can be in this region, you position yourself somewhere down here to the south and to the east, right? Where you have a nice view right into the storm. You're never in danger of that storm coming anywhere near you. You can sit on the road and take all the beautiful photos and videos you want and, you know, do the same thing the next day, right? Sometimes you see those ridiculous chasers on TV, right? And what they often do is they come driving right through this forward portion of the storm. And all that happens is the weather gets worse and worse and worse. Large hail starts, right? So they lose their windshield. And then just as they emerge from that heavy rain and large hail, oh, look, there's a tornado, right? So that's exactly how not to do it. And that's, you know, most certainly not the way that we sort of do it when we take our students along.
Yeah, so a lot of it is sort of forecasting where the storms are going to develop, how they're going to move when they do develop, and then position yourself in that correct location, to sort of to the southeast of the likely path of the storm. And this is what we would see if we were in the field, if we had a supercell thunderstorm going on with a tornado signature. And the signature of the tornado, all of this is rain and hail out in front here to the northeast. And that's the direction the storm's moving. And to the southwest here is that updraft region, most likely where a tornado is going to develop. It's what we call the hook echo. It sort of looks like a fish hook. Oh, that's okay. You can see all of these, you know, this is one individual storm, right? But oftentimes supercell thunderstorms develop in large numbers. We call it an outbreak. And so the next slide shows a pretty famous outbreak back in April 2011. Each one of these red, yellow, and green areas is an individual supercell thunderstorm. And you can see all of them pretty much have that hooked feature. So on this day, you can see all of them rated EF4. Pretty much all of these supercell thunderstorms produce tornadoes of pretty intense nature on this particular day. This was down in Alabama. You can see the border of Tennessee up on the upper part of the slide here, Mississippi and Georgia off to the east. So it spanned over multiple states and very intense tornadoes that were tracking from southwest towards northeast, impacting cities as well as rural areas such as Tuscaloosa and so on this particular day. So what we want to show you is something like what we would see if we were out in the field on the next slide.
If I can just add real quick, Neil, this is a Google Earth image below, and you can see the damage done by each one of these tornadoes from satellite in space, right? So, I mean, there's significant path lengths here, right? And enough damage, wide enough amount of damage that it can be seen from, satellites far away from Earth's surface, right? So these storms, I'm sure, as you all know, are not to be messed with.
So they literally leave their mark, right, as they're moving along in terms of damage. So here is the kind of thing that we would see if we were out in that position to the southeast of the storm, and looking at a supercell thunderstorm. And there's a lot of features that we typically show to the students and pick out, and you'll see some of the photos of some of these from our chases, our individual chase events. And just to point out a few of them, there's one that and these are features that you might likely see in a variety of thunderstorms. Don't necessarily need a supercell, but some of them are sort of classic to supercells. An Anvil Cloud, this is where the storm essentially rises up and starts spreading outward. And these are beautiful clouds in terms of thunderstorms. Very intense thunderstorms, you'll see what we call an overshooting top. This is where that updraft region where the large hail is developing punches up into the lower stratosphere. And so it has grown very deep with intense updrafts, oftentimes in supercells over 100 miles an hour, 150 miles an hour, going straight up in the atmosphere. Some of the features to pay attention to here in terms of where the tornado may develop is what we call a wall cloud. And that's the feature down on the base here, where we see this lowering of cloud base. And that's usually where the tornado would descend from if a tornado develops in a thunderstorm. So that's usually what we're trying to focus in on. Is there a wall cloud? And what you'll typically see is that whole cloud and base of your cloud rotating slowly in a clockwise type fashion. So as soon as you see rotation like that, there's likelihood that you might get a tornado out of that region of your supercell thunderstorm. You can go ahead, Nick. I'll let you pick up here if you want.
Yeah, so thanks. So this is just another sort of cross section through the storm, and I'm not going to spend much time here because Neil did a really nice job talking about it, other than to say, right, that as that air rises and rotates about, right, particles can spend a lot of time in that updraft. And that's how large hailstones can grow, right? Oftentimes they take maybe 1 or 2 trips through this updraft and then can become as large as, say, basketball size in really, really intense updrafts, right? So you don't want basketball size hail, hitting anything really. I can say one time, Neil and I, the first chase we went on, we were driving, we actually finished for the day. We went to dinner, we went to drive to the airport, or not the airport, to the hotel. And in that time, a storm sort of approached us, not a tornado or anything like that, but we started getting golf ball size hail on our van. And we made the quick decision to turn around and go a different way.
That is the case. There are a lot of U-turns when storm chasing, or a lot of 3-point turns on country roads, dirt roads. So
we figured
very skilled at 3 to 5 to 10-point turns, depending on the width of that country road.
And we figured golf ball size hail in an HWS van would be a quick way to not be able to go again. So, all right, so that's enough about the theory, right? Let's talk about sort of our experience, right? Probably the reason why you all wanted to join us. So I'm just going to sort of give you an example, right, from the last time we ran this class, right? So after the 3 days on campus, right, we drive out to the Midwest. And in 2019, right, that involved 11 nights on the road and a total of 6,300 plus miles of driving, right? So after a while, your butt gets a little sore from sitting in those seats, right? So something that most certainly comes with storm chasing is, there is some downtime in the vans and stuff like that. And I see there's a comment in the chat from Eric. Can you predict the formation of a tornado once you see the supercell thunderstorm? And the answer is large part no. I mean, radar is helpful in that they can sense the wind within the supercell themselves, right? Using the Doppler effect, effectively that frequency shift that you hear when you're, a police car drives by you. That's sort of like, ooh, right? That you are very, very sort of accustomed to. Wind can do the same. The radar can do the same thing. If the wind is moving away from the radar, when it sends out the pulse, that pulse will come back a little bit more spaced out. But if the wind is coming at the radar, then that pulse will come back a little bit more quickly. So the radar can sense rotation within the storm itself, but that rotation is often sort of the mesocyclone, or sort of the circulation of the big supercell itself. The radar doesn't have fine enough resolution to be able to pick up a tornado. So once the radar indicates that rotation is present, the National Weather Service will issue a tornado warning, and there's a fair likelihood that that storm will then go on to produce a tornado. But it ends up that just about 1 in 4, maybe 1 in 3 supercells do produce tornadoes. And if you just looked at it on the radar, there's really no way to differentiate which one does which. I mean, really, we need very high spatial resolution measurements. And there are aspects that we, even in 2021, don't really understand. So in 2019, right, we spent 11 nights on the road. You just see some cities, right? You get a really, really nice, cross section of America, and lots of nights in Holiday Inn Express and Comfort Inn, right? And you can see here, this is an image that one of the students drew from 2 chases ago, 2017, just to get a sense of the states we visited, something like 15 states over the course of the 11 nights that we were on the road. So a lot of time on the road, a lot of time to see a lot of sights, and also to see the storms. And here you can see, thought it's important to recognize the students who went along on the chases, as Neil mentioned, right? Between 10 and 15, 18 students. And there most certainly are logistical issues associated with the trip, right? Because you're always trying to think about, where are we going to end up the next night so that we can reserve enough hotel rooms, right, for all of these students. So we're always playing that game, and so there's more than just the weather involved, right? Logistics are a really, really big issue. And in fact, 2021, this was our year to be storm chasing, and in fact, we would be doing that right now if it weren't for COVID. So I guess the storm chasing loss is all of your gain today. So, or I hope it's your gain.
I'm just going to cut in here, Nick, is, sort of our plan when we hit the road is we take off from Geneva. We usually have 1 or 2 vans. The last 2 groups in 2017 and 19, we had 2 vans full of students. We had 4 instructors. So we have those sort of pairs of instructors as drivers for the vans. And then we sort of plot where we're going to be, plan where we're going to be, and make hotel reservations. And then the next day, where are we going to be? We make hotel reservations. Once we get out in the Central Plains and we start forecasting, then we're trying to figure out where the storm's going to be and where are we likely to be for the next day to chase additional storms and make hotel reservations there. So it's really quite a logistical feat to try to accommodate a large group that is constantly on the move.
And with that in mind, so here's a couple of photos of what happens, right? The thing that I love the most about this course, right, is that it's putting the knowledge to use in a real world setting, right? That's what life's all about, right? That's what education's about. The students at HWS, right? They're preparing themselves to go, apply what they've learned to some real world job. And, I can have students, I can teach them about the weather, Neil can teach them about the weather, and then we can have them sort of give a weather briefing where they try to look at maps and identify how all these different ingredients come together on a map. And that's great, right? I mean, the students generally do well for a grade in the course. But here, these briefings ask them to put together all the knowledge they've learned, right? Both in the 3-day intensive course and for some students in many other classes that they've taken in meteorology, right? And these students are the ones leading the briefing. So we assign, based on hotel room, groups of 2 or 3. And it's their job at 7 a.m. or 7:30 a.m. to come in. We bring along a projector and computer, laptop, and they are looking at weather maps, and they are going through sort of a set of ingredients. Where are all these ingredients coming together to likely give us the best severe weather, right? And all the other students, they have tasks as well, right? To, come prepared to ask questions and maybe, question what they've come up with. And Neil and I, of course, have our own thoughts, right? We've talked about this as well, but we let the students come to their own decision. And 99% of the time, the students' consensus, even though it pains me to keep my mouth shut. In fact, Neil will often say, Nick, shut up, right? But it pains me to do that. But the students' consensus, right, is right. And, then we follow their lead. And that's the place we go to for the day, to at least maybe 100-kilometer, 100-mile radius, right? That's sort of our start point for the day. Let's head to City X. We're going to sit there, and then we'll reevaluate what the weather looks like. And you see two of these discussions here. You can see the student here, Aubrey, actually giving the weather discussion with the maps here projected on the wall.
I'm just going to add one thing into that, is that when the students realize that they have to come up with the answer of where are we going for the day, right? That is challenging. They're used to giving sort of a general weather briefing when we're back on campus, nothing's really at stake. But when they have to say, where is the whole group going to jump in the vans and head to so that we see the best storms we can for that day, there's a lot on the line there, right? And so there's a fairly detailed discussion. And I'll mention that we get together at like 7 a.m. in the morning, but students that are giving that weather briefing, they have started looking at things the night before when we gotten into the hotel the night before, and they're looking at it before breakfast, before we all get together, so that they have knowledge that they can bring to the group. So they're working pretty hard in terms of trying to be prepared for that just initial question, where are we going to start the day? Because we're always on the move during the day. We go to one place and then sort of wait and see how the weather develops. And then we, decide, should we stay here or should we move to a new location?
So when we get to that location, right, we bring along a bunch of instruments, right? The students, if we are able to, we bring along our weather balloon system, some helium, right, which is no small feat in a van with 14 students and luggage. But here you can see some students, right? They do everything. They blow up the balloon, they launch the balloon. And in fact, I have a video here of that happening from our chase in 2017. And this weather balloon, right, has instruments via GPS that are relaying back temperature and moisture and wind measurements every second. So we have an understanding of what the atmospheric conditions are like between the surface and all the way up to, say, 20 kilometers above the surface. Yeah, Raywinson, some places they're called radioson. They're similar, not exactly the same, but effectively it's an instrument package that's attached to a weather balloon. The National Weather Service launches them twice a day at about 60 or 70 places across the country. And even with all the great technology we have, satellites, radars, right, so much weather data today compared to 50 years ago, these weather balloon measurements are invaluable, not just for understanding what's happening now, but though that data is ingested in our computer models that help make forecasts into the future better. So here the students effectively are mimicking exactly what professional forecasters do multiple times a day, all across the world. They're launched twice a day at 0 and 12 Greenwich Mean Time or Zulu time.
And this system is great in the fact that the students can see the data coming in directly every second from the sonde as it's rising up through the atmosphere. And it's being plotted to show them how the conditions are changing at different levels in the atmosphere. And we can even use it as we're on the move. So we can pack it all up and we can get the vans moving to a new location, and we can continue to receive that data as the balloon is floating up through the atmosphere.
So in Alaska, I know we have a few minutes left, and then we most certainly want to save time for questions. thought we just show you some of the cooler things we have seen, and then end with the best day chasing of my entire life. And Eric, to answer your question, we typically launch one balloon at a time. That way that the receiver can sort of transmit between the receiver and the car itself. You can, and we did this back in 2013, 2014. Neil and I and a bunch of students were part of a big lake effect snow field project, and 5 different groups had their own systems, different places around Lake Ontario, and we were launching simultaneous, but you need a separate system to sort of communicate if you want to launch more than one simultaneously.
Usually it takes about an hour for the balloon to flow up through the troposphere into the lower stratosphere. So it takes some time to get all that data over that deep layer of the atmosphere.
And yes, Sally, there are one-use disposables. So that is most certainly a money issue, a downside. The National Weather Service, when they launch them, has little placards on them because they do come back to the surface, right? That says, if found, please return to the National Weather Service. I think about 4% of them end up returned. So, not a huge amount, unfortunately. So here's some really cool pictures, right? Upper left here, you can, whoops, I hit the wrong button. Upper left here, you can see the supercell. How this looks similar to the schematic Neil showed. You can almost imagine this entire system spinning. This is in the incredibly well-traveled town of Dora, New Mexico, that had exactly one rundown shack. Down here in the lower left, you can see a great photo of Intercloud Lightning that a student took. One of their favorite things to do when we're watching a storm is just to hold their iPhone up or hold their camera up, and just take repeated pictures until they're lucky enough to capture lightning. This is a pretty impressive photo here. Upper right here, this is in the panhandle of Texas, I believe. And sort of this linear feature you see here is known as a shelf cloud. That linear feature is sort of the leading edge of that thunderstorm, what we call the outflow. And you've experienced this in your life. Think about when thunderstorms come to your house. A lot of times you sort of can hear the thunderstorm before the rain starts. You'll get that gust of wind, and then 15, 20 seconds later, the heavy rain will start. The shelf cloud here is more or less the leading edge of that wind gust, which is coming from air that's descending from the thunderstorm. Effectively, a small amount of the precipitation that falls evaporates, and that causes this air to rush to the ground really quickly. And sort of the wind at the leading edge of these shelf clouds can be 50, 60, even as high as 100 miles per hour in extreme cases.
Yeah, I just mentioned on that supercell in Dora, New Mexico, which I think did have a population sign of 4 people in it, by the way, as we drove through it, is that in eastern New Mexico, we actually ran out of roads on this day. There were no more roads to go further westward on this day. So we literally had to stop on this road and watch the storm, and we couldn't go after it, which was painful at this because it was a beautiful, beautiful storm.
Finally, here in this lower right-hand corner, right, you notice how these clouds, maybe not the best example I've ever seen, sort of the pouch-like shape to these clouds. That's called mammatus clouds. Sort of a rare type of cloud that you can see in sort of thunderstorm environments. And of course, I am never one to turn down a photo opportunity. So we gathered the whole group here and took this photograph here in front of the van. So that brings us to May 28th, 2019, right, which the last chase we went on. And, before we go out, right, we tell the students, right, the whole idea is to learn about the weather. If we see something cool like a tornado, that's a bonus. But we can only take what the weather brings us, right? We have to make decisions about where to go. We have to think safety in mind, right, which sometimes causes us to have to drive away from what might be a beautiful storm. But on this day, right, we began our day sort of in central Kansas, right? The beautiful town of Tipton, Kansas, which I'm sure none of you have ever been to. It's sort of a middle of nowhere place, right? And actually what happened was it's sort of a success via a mistake, right? So Neil and I put it out there to the students, right? And if you notice here on this is a radar image from my phone. So at all times we have radar in the vans, right? I think we didn't mention that, but we have satellite radar. we always know what's going on around us. And if you notice, there are two distinct storms here, right? You can see this little hook shape here and a hook shape here, and the red indicates tornado warning. So about 30 minutes earlier, we're down here near Lucas, and we said to the students, should we go after this storm or should we go after this storm? And, when you have 10 students trying to make a decision, right, there's deliberation. Finally, we decided to go after this storm. Well, we made it halfway up, and then half the students were like, no, let's go after this storm. So we just made a decision. Let's just stop and figure this out, right? So we stopped on a side road. This was our view. And we decided just to let this beautiful storm come at us, right? We were the only ones there. There was nobody else for miles aside from this one house. And unfortunately, the house did lose its barn, but thankfully nobody was hurt. And this storm went on to produce 9 tornadoes over the course of 45 minutes to an hour. And I'm going to sort of show you, Neil and I are going to show you some of the variety of different beauty that it produced, right? Violent, but just beautiful. So this is a sort of a middle of the road sort of funnel, right? Pretty typical, right? You'd recognize that as a tornado. This is maybe my most...
Nick, can you go back to that for a second? Just to point out some of the features. We have what's called a condensation funnel. So this is cloud sort of pointing down to the surface. And then you have a debris cloud near the surface where dust and debris is sort of being kicked up, where the circulation has met the ground and is causing debris to be kicked up and suspended in the atmosphere.
Thank you. A little later on, right? This is that main funnel that Neil pointed out, but every so often, it's pretty rare, but every so often you can get a sort of satellite tornado. And here, watch this, all the way through the cloud, and there's a really, really tiny circulation on the ground here. I've never seen this before in my life in reality, right? It's probably less than 1% of all supercell tornadoes look like this. Very rare.
This is something that when we're out in the field, we're looking at a tornado that's going on. We often get the question from the students, have you seen anything like this before? How good is this tornado? And me and Nick on this day were like, we've never seen anything close to this. This is the best thing we've ever seen. Just to put it in context for the students, like you may never see something like this again in your lifetime. Soak it up now.
Like wedding day, kids being born, tornadoes. Here's another one with our former student, Caitlin Crossit here, taking a photo out the van.
And she was helping run this particular trip in 2019. So she actually went on all 3 of our storm chases. First one as a student, and then the subsequent 2 in 2017 and 19 as a sort of co-peer instructor and one of the drivers of one of the vans.
Here, then, this tornado eventually grew large and became a pretty violent tornado. And this is when we decided to reposition to safety. Again, as Neil mentioned, tornadoes can only be rated based on the damage they provide, right? So this could only get a rating as high as EF2 because it hit effectively a rickety old barn. But likely this was an EF3 or maybe even EF4 tornado at this time, just based on size. You can even see some pieces of debris sort of through the air here in this still shot.
Yeah, and this is what I was mentioning before, is that this particular tornado at this time, we were actually sort of maybe up to the right of this when we were watching it earlier in the day.
We're down this road actually right here.
Yeah, we decided to get out of that area for good reason. And we came off to the southwest or southeast of it. And as we were making that move, we could sort of see inside of that large funnel cloud. And that's where we could see the individual multiple tornadoes, what we call multi-vortex tornado. There was about 4 individual tornadoes inside of that larger one. So it's just another thing that I'd never seen before in real person.
I want to show you the video on the right here. I know we're sort of out of time, close to the end of time here, but I think you can really see this is us repositioning as the tornado was ongoing, right? So you kind of have to walk and chew gum at the same time here, right? So Peyton Caputi, who was another former William Smith student, was helping out along with Caitlin. She was driving. And you can see, right? You can see, even though this is just cell phone video, just how dynamic this storm is, right? Getting larger and larger. So the picture on the left is the storm for the first 30 minutes. The picture on the right is sort of what it became toward the end. And then we have one more video, I think.
Yeah, we try to stay with these storms as long as we can. So that's the chase part of it, right? We position ourselves and sometimes let the storm come to us. And if there's a tornado warning or we observe a tornado, then we get on the chase end of things. And we start to try to position so that the storm, we're out ahead of it, but off to the side, and we can see it go by. And then we reposition to a new spot and let it come towards us and go by again. And we do that as many times as we can so we can get sort of subsequent views of the evolution of the whole storm and the tornado for as long as we can. We were fortunate on this storm to be one of the only ones out in this area for this particular tornado. There are days where there are tens of storm chasers on an individual storm, and it's, you know, a crowded sort of a crowd sort of, you know, trucking along together on an individual storm. But we try to avoid those areas and find our own individual storms that are really good.
You can see here how large this tornado is, right? And this wind that we're experiencing is not from the tornado itself, but it's what's called inflow. It's the air that's feeding into the system to help keep it going. So we had 50-mile-per-hour winds at our back here while we watched this storm pass us by. And it was after this that we sort of decided, yeah, the time was up. We had been on the storm for an hour and a half. We would have had to chase back across the damage path. We didn't want to do that. And we figured our time would be done. So to Eric's question, can you use a drone? Most certainly. There are people who are currently sort of experimenting using drones or other flying objects like that to not only observe, but also take observations within tornadoes. So it's something that there are some groups, Penn State, there's a researcher there named Paul Markowski, who's one of the foremost experts in tornadoes and tornado formation. And him and his team have been doing some of that.
Yeah, so some of the drones aren't like the ones that you sort of are maybe familiar with. They're fairly large and have a substantial weight to them, so that, you know, the winds are intense even in the region of the thunderstorm outside of the tornado. So you'd have to have something that's pretty stable, pretty substantial in terms of collecting those measurements.
To Angela's question, approximately. I'm sorry, go ahead, Neil. Finish your thought.
No, go ahead.
To Angela's question.
No, that was good.
Approximately how close do you get? I would say that sort of in this storm, when the storm was sort of passing us by to our west, we were a couple miles away. You know, that was the goal. Especially a storm that looked like that, right? That tornado was intense, not to be messed with. So as soon as we saw, you know, as it came, we watched it come in, and when it came within about 5 miles, we repositioned out of the way. And at all times on that GPS radar, we can see us and we can see the storm. We can also use our eyes, right? And make sure that we're in a spot that's safe. And we found a pull off from the road about 2 miles further up and watched it go there. So I'd say no more than a couple miles.
Yeah, I will say it's pretty intense. It gets the heart pumping there when you're that close to an intense tornado. You know, and, you know, safety first. And in fact, I can remember on that day that we saw the 9 tornadoes, and especially that big one where we were just a couple miles away from it. We were sitting inside the vans, and the wind rushing into that storm was rocking the vans, right? And some of the students were like, you know, uncomfortable and asking, should we be moving out of this location? And so, you know, part of our job is to make sure that they're comfortable and they're, again, understanding that we're in a safe location, right? And we always position ourselves on the side of the road or on a road where we have a pretty easily exit plan. So we can get out of that area quickly, sort of unobstructed, you know, exit plan.
Gregory, to your question about storm chasing, how long has it been done? It's been done for many, many years. I did it when I was an undergrad student. But, you know, it's two things. It's become easier recently because Now you have data at your hand. So if you know what you're doing, right? If it's like there are professional tours where you can pay to go along with some people who will take you out there, or in a college location, right? There's this, the technology is there to do it safely. Back 20 years ago, you'd have to call somebody who might be monitoring the radar back at a computer. So it was more challenging. I will say, in terms of the public, right? Because today, with a cell phone in your hand, right, everyone thinks they're an expert at everything, right? So in Oklahoma, when a big storm happens, there are hundreds of amateur chasists, whatever you want to call them, who are out and about, chasers, I guess, who are out and about trying to see the tornado. And that does potentially cause an aspect of danger. So Neil and I did almost everything we could at all times to try to avoid what we might call chaser convergence, right? And it was after the movie Twister. The movie Twister really sort of gave a face to storm chasing, and that's when it became something that the public wanted to do as well.
You can literally get in situations where you're out in the middle of nowhere and there's so many chasers on that particular storm that you're in a traffic jam. You're bumper to bumper and you have no exit plan and can't move, essentially. And that is a pretty unsettling, dangerous situation that we don't put ourselves in. I know there was a question. Yeah, go ahead.
Sally's question about global warming. Neil, you want to take that one? I can do it too, but I give you a shot.
Yeah, I'll take that, because actually we just developed a course on climate change science and offered that in the spring semester. And part of our discussion we spent on reading research articles on how convective storms are being changed by changes in climate. And one of the articles was on how tornadoes, the numbers and the intensity are changing. And in fact, what's happening is not so much the numbers of tornadoes we're seeing each year is not really increasing, but both the intensity is increasing in terms of the tornadoes. In other words, they're becoming more damaging and stronger in terms of that enhanced Fujita scale that we talked about earlier. And on days when there are tornadoes, more tornadoes are happening on those days. There's fewer days where you're going to see an individual one or two or small number of tornadoes. But on a day where you have tornadoes occurring, generally you're getting these larger outbreaks for large numbers of severe storms that are producing tornadoes. So that's sort of the direction, the impact that we're seeing in terms of the science and how tornadic thunderstorms are changing, at least across the US, where we have some of the best observations of these kind of storms. And we actually see a fairly high frequency in terms of the US compared to other places in the world. US sees a huge frequency just because of the natural conditions of the atmosphere that we have, the large scale weather systems, and some of the geography sets up an environment more favorable for convective thunderstorms. So in the US, we typically see on the order of, that are observed, anywhere from 900 to about 1,800 tornadoes per year. And that's going back in numbers from about 1995 through 2020, so just last year. Last year, we saw a little over 1,200 tornadoes were observed around the country.
I just want to add one more thing at the end here, and then if anybody else has any questions, I'm happy to stick around. I don't know, Karen, how much long do we ever overtime?
We're scheduled to write 12:45, but this is great. So
if others, I'm happy to stay until, after 1 o'clock. I think I'm on overtime then, so my pay doubles. But maybe I'll let Neil talk about this last flight, since he was the one who was contacted initially about it.
Yeah, this was great. This sort of shows, I think, the network that HWS has pretty much everywhere around the world, around the country. When we got back from storm chasing in 2019, Kathy Williams and the folks in the communications office, worked with us to put together a This Week in Photos on the HWS website. And so we had a week devoted to all the incredible photos that we took during our storm chase that year. And we posted it up there. And lo and behold, one of our alumni that are from William Smith 91, Rachel Thomas Medwid, contacted me out of the blue one day. I received an email and she says, I work for the American Meteorological Society as one of their media relations and news editors. And I saw the TWIP photos. They were just amazing. Would you guys want to submit one of those photos as part of a photo collection that we do in one of our monthly publications? And I said, oh, you bet we would. So we worked out, chose the photo, and this was one of our fantastic group shots, selfie shots with all the group members, students, and drivers and everything there, with a great sort of shelf cloud thunderstorm at our back there. You can see the wind blowing our hair all over the place. And this was just a great group shot, and we got it published, and great recognition for the colleges, great recognition for, the students in terms of their participation, and the geoscience department. So that was just sort of a great way to top off that particular storm chase. Yeah, I think we'd be happy to take other questions if folks want to stick around, or if there's, other questions that you'd want to learn about or know about. Me and Nick be happy to sort of talk with those. I know there are other reunion events going on, so don't miss any of those. But if you're curious and you feel like asking, just please go ahead.
And I'll just mention a couple things are added to the chat. So to Eric's comment that he lives east of Albany, Vermont, and they had a tornado warning a few months ago. Most certainly, although somewhat rare, right? The Northeast is not without tornadoes. Maybe relatively famous recently, Springfield, Massachusetts had, I believe, an EF3 in maybe 2011, right? There have been a couple other ones through that region as well. So it's pretty rare, but it's most certainly not unheard of. And just to follow up by Sally's question about, will they start showing up in places which had not frequent tornadoes in the past, or does basic geography preclude? I guess I would just add, right, that, when teaching students about tornadoes, right, there are ingredients that are important, right? And sort of over the Midwest, right, those ingredients come together most favorably, right? You have high moisture from the Gulf of Mexico. You have some important contributions from the Rocky Mountains to the west, right? So the U.S. geography is such that although we only have a small percentage of landmass, we have like 75 to 80% of all the tornadoes globally, right? So there's some places where likely you're never, unless something drastic happens, right? You're likely never to see huge changes in frequency, right? But there is some research that has shown that the tornado alley that's, typically Texas, Oklahoma, Kansas, Nebraska, might be shifting a bit eastward in the last, say, 40 years to sort of Alabama, at least increasing frequency, Alabama, Mississippi, Arkansas, places like that. So I'd say subtle changes, right? But I don't anticipate, all of a sudden Boston becoming the tornado capital of the United States or anything like that.
Yeah, I'll just add on to that, because actually, with the climate change science class that we taught in the spring, we read another article, right, that looked at how that area across the US may or may not be changing in terms of tornadoes and where it's sort of located. And Nick's right in that we have this area typically that is well known as Tornado Alley, sort of the central part of the US, right? And this study showed pretty convincingly, with observations of tornadoes over many decades, that what in fact is sort of happening is that tornado alley is still very active, but it's sort of expanding in its area rather than sort of shifting entirely to a new area. So more places haven't seen the large numbers or intense tornadoes are sort of seeing those on sort of the fringes as that area expands. And the southeastern US is definitely one of those areas.
Anything else that anybody is wanting to know, or, you know, we sort of batted around the idea of maybe doing an alum chase. There might be some heavy lifting by folks that are not named Nick Metz and Neil Laird to make that happen. But if any of you can lift heavy things like that, you know, that's a possibility.
And if you feel like, you know, being in a van for, you know, 11 days straight, or, you know, 10 days straight, and driving, you know, over 6,000 miles, if that sounds really good to you, then maybe you're a storm chaser at heart.
And as an added bonus, you get to hear all sorts of stories over and over again about my 8 and 5-year-old kids. So, you know,
with no guarantees that you're going to see a tornado in those 10 days either, right?
But you will hear the stories.
No guarantees.
I love it. That's great. If everybody would like to unmute and just give these two a round of applause, that was excellent.
Hey, thank you, everybody.
Thank you.
Thank you
Hey,
all.
Caitlin.
Bye.
Good to
Be
see you.
well.
Thank you so much.